Hello. So now we will proceed further with the asymptotic normality. So as we recall, asymptotic normality uh, from the earlier video, we know that um, if we were to treat an estimator as a random variable, right? Then this estimator, um, the distribution of its estimator will converge to normal, okay, with mean um, with its mean being the true value or say true value of the estimator is trying to estimate, and its variance basically uh, is equal to 1 over n uh, multiplied by the facial information with respect to theta. Okay. Um, I would say that uh, the last video was, quite involved, I would say, and the examples are much easier to work with. Okay. All right. So that being said, we proceed with some example as we do earlier, where we use the exponential distribution. Okay. Okay. Suppose we have a PDF of an exponential random variable. Okay. So we will have 1 over theta exponent x over theta. Okay. X is greater than 0, and theta is belonging to the parameter space, where this parameter space is just all values greater than 0. Okay, let's see if we have uh, this value here. So we want to find the asymptotic distribution of x bar. That is the sample mean. Sorry, that is the sample mean um, associated with the MLE, right? Since the sample mean is the MLE of x. Okay. The way we do it is simple. We just do it like this. Okay. First, we take a log. So when we take the log, we will have log theta minus uh, x over theta, right? And then differentiate this with respect to theta. Okay. So what we have 1 over theta x squared, sorry, x over theta squared. So, right, so far. Now, integrate this again. Integrate this again. Sorry, differentiate this again with respect to theta. And you will have 1 over theta squared minus x over theta cubed. Uh, yeah, and then should be multiplied by 2 here. Okay, so you have this. All right, now take this expectation. Okay, so take this expectation and you negative it. Yes, you will have So you will have the expectation of this. Notice I negative it. There's a negative sign here. Okay. So I just bring the negative sign side, and then I will have this thing. Turns out this equation here turns out like this. Sorry. Okay. So now we see that this is constant and this is also constant. So we can just bring these out, and then we will have 2 1 over theta squared negative 1 over theta squared plus 2 over theta cube expectation of x. Okay. So what is the expectation of x? Uh, if you recall, if x here, if x has a PDF of this, then expectation of x is theta itself, right? So you will have negative 1 over theta plus 2 over theta cube theta. So these two cancel out, and you will have 1 over theta squared. Okay. So for this expectation, this is the theta squared here, and this will be your Fisher information. It's just Fisher information. Okay. So from the example that we worked on from the last video, right? We know that x bar converge to normal. The distribution converges to normal with mean theta. Sorry, with mean being the expected value, right? Which means theta itself. And then the variance, of x bar being the uh, 1 over n multiplied by the Fisher information. Okay, you don't have to actually write these two. You just write it so that it's easier to reference, right? And so this is just uh, n theta 1 over n 1 over theta squared, and this is just n normal theta theta squared over n. Now that is the uh, asymptotic distribution of x bar. So x bar converges to normal with mean theta and variance theta squared over n. Okay. Now note that as a property, just some hindsight lah, about this whole asymptotic distribution thing, right? So as the sample size gets larger, right, as your n gets larger, um, you know, this thing here, this n here, also gets larger as well, which means that the variance here will tend to this variance here will tend to 0 as an infinity, right? And if n tends to infinity, turning the variance to tend to 0, what that means is that if the variance is 0, then the value itself is a constant. True. So here we can say that, that's just another way of saying this value of x bar here will converge to it, okay? Because the variance decreases until at one point becomes 0, okay? Meaning it has already being the same, it has already converged to the true value that it's trying to estimate. Okay, all right. Okay, right.
Okay, so if you have a if you have a maximum likelihood estimator, theta hat, right? Then the variance of this estimator here, the variance of this estimator is the lower bound. Okay, so lower bound for the variance of every other unbiased estimator of theta. Okay, so let's say that maybe we have another estimator, right? We don't know how we get it, but we know that we have a certain other unbiased estimator. Let's call it maybe phi. Okay, now if this phi here, okay, phi here, we know that it's an unbiased estimator, right? But if the variance of phi is equal to that of the variance of theta hat, right? Then what this implies is that there is no better estimator. Okay, there is uh sorry there is no better estimator, in the sense that the variance is as lowest as it could be, right? And you wanted to find an estimator with the lowest variance. Okay, so that because the variance ni is in a way macam like a measure of error, right? And you don't really want that. And then okay, so we cannot have a better estimator lah. Okay, so what that means is that this estimator is the best estimator, in the sense that you can say phi or maybe theta hat is the MVUE, also known as the minimum variance unbiased estimator. Okay, alright, so in the limit, the maximum likelihood estimator is this type of best estimator lah. Okay, okay, now let's proceed with another topic. Okay, Rao-Cramer inequality, which is the Rao-Cramer inequality. Okay, first was some motivations for the before we start. Basically, we need to find one of the applications of the Rao-Cramer inequality is so that we can measure a property of maximum likelihood estimator, of estimators in general, that we call as efficiency. Okay, so the efficiency here says that so the efficiency is basically the ratio. Bear with me, I'll just explain it without words, but I'll write it later. But it's simply the ratio of the Rao-Cramer lower bound to the actual variance of any unbiased estimator. Okay, and an estimator with an efficiency of say 50%, right, means that it requires around 2%. It requires, sorry, not 2%, around 2 times as many sample observations to do as well as an estimation as can be done with the minimum variance unbiased estimator, which is having a 100% efficiency rate. Okay, But that's we'll revisit this topic later. Okay, so let me just proceed with the inequality. um, okay, so let x1 x2 okay xn, okay, let this denote a sample with PDF fx given theta, where theta belongs to the parameter space. Okay, and this parameter space is specified like this. Okay, and support of x, the support of x does not depend, it is independent of theta. Okay, okay, so that we can differentiate with respect to theta under integral signs. Okay, if y, which is a function of the sample here, is an unbiased estimator of theta, okay, then the Rao-Cramer inequality states that okay, Rao-Cramer inequality states that the variance of y is greater than 1 over n, and this integral here, okay, d log fx. Okay, yeah, okay, 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 then the variance of y, which is that unbiased estimator, is greater than or equal to this integral here. Now this is just official information, but interpreting it this way might be harder, so we'll just change it to the usual form that we used in the previous example, which is negative 1 over n, okay, del square ln fx over del square del theta square fx given theta dx. Okay, and this inequality here is what we call the Rao-Cramer lower bound, or RCLB in short. Okay, alright, okay, now as earlier said, these integrals here is just now this is just the expectation, right? This here, okay, and for this one it is just this, and these are just the both of these are equal, right? And they're just the Fisher information. This is simply the formula of the Fisher information. I have yet to state what is the definition of efficient information, and the definition is simply um, the expected value of the score uh, function squared. Yeah, that is the definition of the efficient information, which is just these two integrals here lah. Okay. Right. Okay. 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 Okay, so returning back, let's proceed with the example. Okay, so if we were to return to our original example with the exponential PDF, right? Okay, let's say we have the exponential sample, we have a sample with exponential PDF, this. I'll just leave out everything else because it's just the same details, right? So if you want to find the Rao-Cramer lower bound, okay, first we find the expectation of x bar, which is just 1 over n sum I equals 1 until n bxi, and the samples here we note that it is IID, independent and identically distributed. It's exponential, so we can just replace it with theta. That would mean 1 over n multiplied by n multiplied by theta, and we have theta. So we say that x bar is unbiased. Okay. Okay, so for the second derivative, right, just find second derivative of the log of PDF, which is just 1 over theta squared minus 2 over theta cubed, which implies that the expectation of the expectation of the second derivative, okay, is just the ratio, okay, 1 over negative 1 over theta squared. Now Rao-Cramer lower bound is just the Rao-Cramer lower bound is just this, okay. Variance of x 1 is equal to 1 over negative 1, sorry, 1 over n negative 1 n negative 1 over theta squared, so it's just theta squared over n. So you have variance of x is greater than theta squared over n, and this is your thing here. This is your Rao-Cramer lower bound. Okay. Okay. Right. So that's about the Rao-Cramer lower bound. I think we can proceed with another example. Okay. If we were to have a random variable, let's say we have a random variable x, and its PDF is fx equals theta x theta minus 1, okay, where x is between 0 and 1, and the theta is can take any value greater than 0. Okay, so we wanted to find the Rao-Cramer lower bound for the variance of an unbiased estimator. Okay, so we will have this thing. As usual, we would take the log of fx, and we will have log theta plus theta minus 1 log x, and then the derivative with respect to theta would be 1 over theta plus log of x. And so our second derivative is just negative 1 over theta squared, and our expectation for this second derivative is just the second derivative itself lah, sebab it's not it's a constant. Okay, so Rao-Cramer lower bound is variance of x is equal to or greater than theta squared over n, or you can just say it's just or you can say the Rao-Cramer lower bound is theta squared over n, right? If you note that this all that I have done so far is just follow back the previous example here. Okay, as you can see here, this is just the same as what we've been doing right now. So this is the Rao-Cramer lower bound. So any variance of x of an estimator, any variance of an estimator of theta, right, would be greater than or equal to this thing here, theta squared over n. Okay, alright. Also, from here we can also find the MLE. Okay, we can also find the MLE by summing up the derivative of the first derivative, summing up the first derivative of the log of the PDF. Okay, so if you have the derivative of log of the PDF being this, okay, then if we were to sum this, okay, from 1 to n, which means you denote the sample lah, okay, and then we equal it to 0, then we can find our MLE, which is just n, okay, negative n sum of I equals 1 until n log xi. Okay, and this is just the want to simplify it further, this is just log pi xi. Okay, now why does this work? Because recall back the definition of the likelihood function. Okay, think where is that? here, this this definition here. Basically, we're taking the sum of this individual x's, right, from 1 to n to denote the sample, and this is just the derivative of the log n function. So if we were to equal this to 0, if we were to equal this sum to 0, that would just be the same as that would just be the same as finding the maximum of the likelihood function. Okay, so if we were to take y I equals to negative ln xi, and this yi here is greater than 0. Alright, so by the change of variables, the formula for the change of variable is fy equals fx, okay, divided by dx, okay, dy. But and this here, this is the absolute value, but you have to express this value of x in terms of y. Okay, so if y, your y here is negative ln xi, that means xi here is exponent, okay, raised to the power of negative y. Okay, so you use this term here, use this term to describe x. Alright, so you will have theta exponent y, okay, to the power of theta minus 1, raised to the power of theta minus 1. Let me check. Okay, similar to this, and you multiply it with the absolute value of the derivative of this. Okay, so dx dy is just negative e to the power of y, so negative e to the power of negative y, but this is the absolute value, right? So you'll just have theta e y theta plus 1 multiplied by e to the power of negative y. Okay, and this e to the power of negative y cancels with plus 1 here, so you have theta e raised to the power of y theta. Okay, and theta here is greater than 0. Now if you remember your distributions, right, what this PDF shows is that this PDF here, okay, this PDF here is actually a PDF of an exponential distribution with mean 1 over theta. Okay, so you can say that y is actually exponentially distributed, where the mean is 1 over theta lah. Mean 1 over theta. Okay, and if you still can recall from your Prof Stats 1, if yi is an exponentially distributed random variable with the mean 1 over theta, then the quantity u, which is the negative sum of all the yi, is gamma distributed, okay, with parameters n and scale parameter being the earlier 1 over theta, as we have shown earlier.
Okay. And from here we can proceed with finding the expectation. of our MLE. Okay. Um, so as we know, our MLE is given by this here, and from here we know that this bottom expression here, this bottom expression here corresponds to U, and U here um, is distributed as a gamma distribution with parameters n and 1 over theta as a scale parameter. Okay. Uh, so if we were to find the expectation, then we can just simply expand lah, you know? Theta hat into n over u. Okay, because this here, theta hat is equals to n over u, where u is negative log, negative sum of log of the random variables. Okay, then this corresponds to the integral n over u. Okay, integral n over u, and then the PDF of gamma uh, distribution. Okay, so what is the PDF of your gamma distribution? It's 1 over gamma n, 1 over gamma n, 1 over theta raised to the power of n. Okay, and by u n minus 1 e negative u over 1 over theta. Okay, du. Okay, then simplify. If we were to simplify, we know that this value of n here, n we can just bring out, and 1 over u, that leaves us with 1 over u, multiplied by 1 over gamma n. Okay, multiplied by theta to the power of n, u raised to the power of n minus 1, and exponent raised to the power of negative u theta du. Now, if you combine the two terms u here, you will have n, okay, integral 1 over theta n, 1 over gamma n, okay, multiplied by theta n, u n minus 2, exponent u theta, negative u theta, du. Right, okay, now the integral has got a bit more, let's say a bit more complicated, in the sense that we don't really have an easy way to solve this integral here directly. So what we can do is we can apply a very, you can say a nice trick lah, so to speak, towards this integral here in order to solve this integral, find the expectation. So what we'll do here is we multiply this integral by n minus 1, gamma n minus 1 over gamma n minus 1, essentially multiplying by 1. And we express theta as theta n minus 1 over sorry, so multiplied by multiplied by theta, sorry. Okay, so apply these two steps. Okay, that would leave us with n integral sign gamma n minus 1 gamma n minus 1. Okay, Okay. Um, theta n minus 1 multiplied by theta multiplied by u n minus 2. Okay, so for this u n minus 2 here, let's write it as n minus 1 minus 1. Okay, and u and, and e multiplied by e negative u theta du. Okay, so now we apply another step, another trick, and by making a few observations. Okay, so now we note that this here, this is constant uh, with respect to u. Same goes with this one, and also gamma n. Okay, so if we bring them outside, we will have this. Okay, we bring all the constants outside, right? Only the selected ones. Okay, we will have this. We will have n multiplied by the ratio of gamma n minus 1 over gamma n divided by theta, then followed by the integral. Okay, 1 over n minus 1. Okay, and for this theta here, let's write it as 1 over 1 over theta n minus 1. Okay, so we can write this as 1 over theta n minus 1 followed by u n minus 1 minus 1, since it's originally n minus 2 here, but we will write it as n minus 1 minus 1 e u over 1 over theta, as we rewrite it earlier as before, as you can see here, du. Okay, so now if you know your distributions, right, this here, right, this is just the PDF of a gamma distribution with parameter n minus 1 and scale 1 over theta. And so if this is the PDF here, if this is the PDF, right, and it's integrated along the entire support, which is u greater than 0, means u is between 0 and infinity, that would mean that the entire PDF integrates to 1. So now we have n uh, gamma n minus 1 gamma n over gamma n theta multiplied by 1. And this is simply n minus 2 factorial n minus 1 factorial over theta, multiplied by theta. And this is just n over n minus 1 theta. And this is our expectation that we wanted to find. Okay. Now, okay, some observations about this expectation here. We can see that this is not uh, theta itself. So we can say that theta hat is biased. And for the variance, I will just state the variance here, but it can be computed using this formula. Okay. All right. But from here, I will just state it because too it's too complicated now, the integral, which is just the square multiplied by n square over n minus 1 squared n minus 1. Okay. Um, Okay, I think here we can just write it as some kind of theta square and square and minus 1 cube. Okay, so what can we say about the um, what can we say about these two quantities, these two uh, quantities here, the expectation and the variance, right? We can say that as n approaches infinity, okay, um, the expectation will approach theta itself, because the n minus 1, the n over this ratio, n over n minus 1 itself, which is 1. And also the variance here will approach theta squared over n. Why? Because this ratio n squared over n minus 1 cube, if I'm not mistaken, converges to n squared n cube, which is just 1 over n. Okay, so as the sample size gets larger, what we can say is that this maximum likelihood estimator achieves the lower bound, the Rao-Cramer lower bound. Okay, uh, Rao-Cramer lower bound in the limit. Okay, because as n gets larger, uh, the estimator approaches normal with mean theta, variance theta square over n. Okay, now we return back to the original motivation, at least in this course, to find the Rao-Cramer lower bound, which is the concept of efficiency. So I'll just read the text here. Okay, just read it again. So if you want to measure the value of estimators, the variance of these estimators will be compared with the Rao-Cramer lower bound. Okay, so the ratio of the Rao-Cramer lower bound to the actual variance of any unbiased estimator is called the efficiency of that estimator. An estimator with an efficiency of say 50% means that you need twice as many sample observations in order to do well in estimation as can be done with the minimum variance bias estimator, which has a 100% efficiency rate. Okay, so I want to state the formula. The efficiency of an estimator equals the ratio of the Rao-Cramer lower bound over variance of y. Y is your estimator lah. Okay, multiplied by 100. Okay, all right. Okay, let's proceed with one example. Okay, if you have a random sample that is IID Poisson with parameter lambda, okay, then you can rework it as I did earlier and derive the maximum value estimated to be also the sample mean. Okay, okay, it's just sample mean. Okay, I'll use this notation just for reference. Okay, so this statement here implies this lah. Okay, now so that is efficient. So that lambda hat MLE is an innovation estimator of lambda. Okay. So, mm, so we can easily do that by just first we compute the mean. Okay. Sorry, not the mean, the expectation of the sample mean, which is just the mean itself, which is lambda. So X is unbiased. And you also can compute the variance. Now, the variance is just 1 over n sum of x, I. Okay. And but you bring the n out, and then you will have uh, since the of course repeating the same arguments before, since the sample is IID, Poisson distributed, so you will have n variance x here. Okay, since the variance across x is across all values of I from 1 to n be the same, so it's just n times the variance of x in general lah. So, and the variance of x is the same as the mean. So 1 over n squared n lambda. So lambda over n. Okay. So now find the Rao-Cramer lobang. Find the Rao-Cramer lobang. Okay. Uh, First we take the log of the PMF, and then we will have this, right? Okay. This here is just the log in case I should, if you want to recall, the PMF of a Poisson random variable is this. Okay, where x is 0 and also natural numbers lah. And your theta is greater than 0. Okay, so now that you have the log of the PEDF, sorry, the PMF, so you find the second derivative. Okay, first we find the first derivative, which is just x over lambda minus 1. And then the second derivative, you can use log or ln. It won't make any difference here. I guess just to make it nicely, just use 1. But at this point, if you use log, it no longer means base 10. It means simply as ln, you know. So the difference is negligible, to say the least. And also this should be with respect to lambda. This is also with respect to lambda. So you will have x over lambda squared. Okay. And then you find the expectation of the second derivative. Okay. And okay, and this is just negative 1 over lambda squared ex. Now x is Poisson distributed, so you will have lambda itself, right? So 1 over lambda squared multiplied by lambda, and you have negative lambda, a negative 1 over lambda. And your Rao-Cramer lower bound would be negative 1 over n, 1 over n plus the Fisher information, which is just negative 1 over lambda. So n 1 over lambda, negative 1 over lambda, which is lambda over n. Okay, so now compute the efficiency. Efficiency is just Rao-Cramer lower bound multiplied by variance of the estimator multiplied by 100. So just plug in the values that we computed above. So Rao-Cramer lower bound is lambda over n. Variance of x bar is also lambda over n multiplied by 100. So you have 100%. So the efficiency is 100%, right? So we can say that x is an efficient estimator of lambda, and therefore x is um, the minimum variance unbiased estimator. Okay, so here we can say that x bar is the best estimator lah of its kind among all the unbiased estimator. Okay, now with that being said, we have covered most of the topic. Okay, we have covered most of the topics under the topic of maximum likelihood estimation. And for the next video, we will proceed with the final, at least in this course, the final property that we involves the estimator, which is consistency. Okay, thank you very much.